Let's go. All right. So I feel like I'm gonna have these awkward one-liners every time I start a lecture every time now. Okay. So any questions on anything from last time, or just in general? Any quick homework questions you want to talk about? Okay. Cool. So a few things. So, as you probably saw in the email I just sent like 5 minutes ago, the Lesson 2 video is finally up on Brightspace after almost 48 hours. Thanks, ITAP. So as a result, since there's a weird delay in the homework of the Lesson 2 video, the homework 2 is going to be extended to Monday at 11 p.m. So, nice bit of extra time to do all those computations. Quiz 1. You may have gotten an email about this, but it's going to be on 9 a.m. The window to take Quiz 1 is going to be on 9 a.m. on September 2nd to 9 a.m. on September 3rd. And it will cover Lessons 2 and 3. And you may have also gotten an email about extra credit opportunity. It gives you an idea of what kind of structure you should expect for the quizzes. And even though it is 10 minutes, it only takes like a minute or two to actually do that thing. So I would say do it so that way you have 2 extra credit points for the end of the semester. And it's available till 11 p.m. on August 31st, which is this Monday. Okay, cool. Any questions on that? All right. So let's talk about trying to find limits graphically. So let's recall the following from last time. So the limit as x approaches c of f of x, that was the one-sided limit that corresponded to approaching c from the right, as denoted by our positive superscript. So the limits of f of x as x approaches c from the right. So in this case, that corresponds to values of x that are slightly larger than c. So x equals values slightly larger than c. And then for the limit as x approaches c with this negative superscript, that's the same idea as above, except instead of approaching from the right, we instead approach from the left. So I'm just going to put quotation marks here because it's the same thing, except just replace right with left. So in this case, x is going to correspond to values slightly smaller than c. Okay? Now keep in mind, with limits, you're letting x approach a particular value, but you're not actually letting x equal that value. So I'm going to put this in all caps, but not equal to. So what that means is that x equals values slightly larger than c, but they're not equal to c for the right side limit, and then a similar thing for the left side limit. Okay? And then we also talked about the idea of a general two-sided limit, in that it exists if the one-sided limits, x approaches c from the left, f of x, and the right side limits, x approaches c from the right, they have to exist and they have to be the same. Exist and are equal. Okay. So last time we talked about if we have an explicit expression for f of x, we can plug in values of x extremely close to a particular value c, and then use that to deduce the limits that we want. But today's lesson is going to focus on if we have a graph of our function here. So how do we figure that out? So if we have a graph of y equals f of x instead, we can think of limits in this case as the height slash y value that f of x approaches as x approaches c. Okay. Get my colored pens out because we'll need them in a second. Okay, so if we evaluate limits given a graph of f of x, there are some ways we can sort of visualize what goes on in these graphs. So there are some general cases that we have to consider here. So one such case is the idea of continuity at x equals c. So we say that f of x is continuous at c in this class if f of c is defined. That's the first criteria. B, the two-sided limit has to exist. Limit as x approaches c of f of x has to exist. And c, perhaps most importantly, these two expressions have to be the same. The limit as x approaches c of f of x has to equal f of c. So these two things have to be agreeing with each other. So in this class, one way you can sort of intuitively think about continuity is to ask yourself the question, can I draw the graph of f of x around x equals c without having to pick up my pencil at all? So can I draw graph around c without picking up a pencil? Okay. So to give you an idea of what that graphically looks like, let's go ahead and do this. So let's draw c right here, and then let's put f of c right here. So then that means that their point is going to be right around here. So that means we have our point c comma f of c. So that automatically gives us criteria A off the bat, so that's good. But now we also have to say, all right, well, our two-sided limit has to exist as well. So if this graph of f of x approaches c from both directions, well, not only do they have to approach the same y value, but they have to approach the function, specifically the function value f of c. So what I mean by that is that we have the left side limit approaches f of c, and then the right side limit also has to approach f of c. So to give you an idea of what the intuition part here, what that says is that can I draw the graph around c without picking up my pencil? So it turns out the answer to that question is yes, because I can just draw this graph around x equals c, and I don't have to pick up my pen or pencil at all. So in this case, we do have continuity at x equals c here. So graphically, that's the idea behind continuity. So any questions on that before we move on to the next page? Okay. So now that we have this idea of continuity, let's talk about the types of discontinuity that one can encounter. So the first one we'll talk about is this idea of a hole. Now the idea behind that is that we have that criteria B from the definition of continuity is fulfilled in that the two-sided limit exists, but it doesn't equal f of c for some reason. So limit as x approaches c of f of x exists, and for the context of a whole is finite, but doesn't agree with f of c. So what does that graphically look like? Well, for a whole we have, okay, well, if we focus on x equals c right here, then the function up here approaches c at some y value, and then the right side limit approaches the same y value. So the two-sided limit exists perfectly fine, but it doesn't agree with f of c for some reason. And that could be for one of two reasons. One, f of c is undefined, so the limit as x approaches c in this case of f of x, which simply corresponds to this y value here. So that would be the first way in which we could have a whole. The second way is that if f of c were defined, but it just doesn't equal the two-sided limit. So what happens in this case is that we still have limit as x approaches c of f of x, but f of c is just somewhere else. So just right here, for instance. So it doesn't agree with f of c here. So in this case, well, in that case we end up with the limit as x approaches c of f of x. It just doesn't agree with f of c, even though these two values are explicitly defined / exist. Okay? So that's the idea of a whole. Now for a jump, the idea is that the one-sided limits exist and are finite, but they just don't agree with each other. So limit as x approaches c from the left of f of x, and the limit as x approaches c from the right of f of x exists and are finite, but the two-sided limit does not exist. Okay? So what does that look like, graphically speaking? Well, that says, all right, well, let's say that we have this function that approaches some y value from one direction, but then we also have that if we approach that same value of c from the right, then we go somewhere else. So the idea behind a jump says, okay, well, we approach the function from one direction, it doesn't agree with the value of the limit as x approaches c from the right if we go a different direction. So in this case, we would have, well, one example of a jump would be where this happens, where f of c undefined, or we could also have the situation where f of c is defined, but it can only agree with, at most, one of the one-sided limits. So what we have is that, for instance, we could have something like this, or we could have something like this. So in that we have f of c is defined, but it doesn't agree with at least one-sided limit. Okay. So that's the idea behind a jump. Now for a vertical asymptote, two things have to happen. F of c has to be undefined, and the one-sided limits of f of x, and limit as x approaches c from the right of f of x, are plus or minus infinity. Okay. So there's three sort of general scenarios in which we could get a vertical asymptote, graphically speaking. Okay. So one such scenario is that if we have x equals c, right here, the limit as x approaches c from the left is going to shoot up to positive infinity, but the limit as x approaches c from the right is going to shoot down to negative infinity. So, as a result, well, we have that the limit as x approaches c from the left is positive infinity, but the limit as x approaches c from the right is negative infinity. Well, what does that tell you about the limit as x approaches c of f of x? So one-sided limit equals one thing, but the other one-sided limit equals another thing. Does not exist, right? Okay. So that's one sort of fundamentally different scenario in which we could get a vertical asymptote. Another one is if we have vertical asymptote at x equals c again, but in this case, both one-sided limits shoot up to positive infinity. In which case we get that the limit as x approaches c of f of x would equal what? Yeah, just to infinity, right? So that's scenario number 2. And then scenario number 3 is when we get something like this, where both one-sided limits shoot down to negative infinity. In which case we get that the limits as x approaches c of f of x, by similar reasoning as this scenario here, is just negative infinity. Okay? Now, there's another similar scenario in which, we could have the one-sided limits here shoot down to negative infinity, but the right-side limit shoots up to positive infinity. But that's just another scenario in which we could get a vertical asymptote. So these are just some examples of which we could obtain a vertical asymptote. Okay? Any questions on that before we move on to our example? Is anyone still writing this down? Okay, I'll wait a minute so that way you can write all that down, because I want to move on to example 1, which will take a whole page. Good? Okay. Anyone else? All right, cool. All right, so I'm only going to have one example today, because once you understand what's going on in this example, then you basically have an idea of how to do the homework in general. So we have this graph of f of x below, which I am not going to find an explicit expression for because just no. Find the following if they exist / are defined for each of these 8 values of c here. So we need to find the one-sided limits, the general two-sided limits, and then the function value. And then once we have those, state whether f of x is continuous at c or classify the discontinuity there. Okay? So let's start with -7. So we have the limits as x goes to -7 from the left of f of x. The limit as x approaches -7 from the right of f of x. The limit as x approaches -7 of f of x. And then f of -7. So let's first focus on -7 and find these 4 values for that value of c. Okay? So, let's do this. So if we take a look at where x equals -7 is, so we have -1, 2, 3, 4, 5, 6, 7. We notice that we're looking right about here. So let's first focus on the left side limit. So if we block off the right side for now, then if we notice that we approach -7 from the left, what is the y value that f of x approaches?
-3.
Yep, -3. Good. So that's the right side limit. Now let's take a look at the that's the left side limit. Now let's take a look at the right side limit. So if we approach -7 from the right, well, what y value do we approach here? Let's give someone else a chance. What y value are we approaching in this case? -3 again. Good. So then, what does that tell you about the general two-sided limits? -3. Good. And then the function value is what at -7? -3, right? Okay. So that gives you those 4 values, which is good. So what does that tell you about the continuity / discontinuity at -7? So first off, do we have continuity at x equals to -7? Okay, good. Why? Why do we have continuity at -7?
Because from both sides of the function where we're trying to find the limit, they're both continuous lines going, and there's no breaks, asymptotes, or sharp turns.
Right. So that's one way you can think about it, but another way you can think about it is that if we harken back to our definition, well, let's take a look at the 3 criteria. So f of c is defined, check. The two-sided limit exists, check. And then the limit and the function value both agree with each other. So that's check there as well. So since all those 3 criteria are fulfilled, then we have continuity here. Continuous. Okay. So if we have that the two-sided limit and the function value exist and are equal, then continuity. Okay. So that's for -7. So any questions on that before we move on to our next value of c? Okay. So now let's do the same thing for -4. So let's write all those down. X approaches -4 from the left. The limit as x approaches -4 from the right. The limit as x approaches -4. And then f of -4. F of x, f of x, and f of x. Okay. So now, let's see what happens here. So let's again first focus on the left and right side limits. So in this case, 1, 2, 3, 4. So -4 is right here. Okay? So if we were to focus on the left side limits, well, what y value are we approaching as x approaches -4 from the left?
-3.
Yep, -3. Good. Now let's do the same thing for the right side limits. So if we approach -4 from the right, what y value are we approaching now? 1. Good. So that means our right side limit is 1. Oh, but hold on. What does that tell us about our two-sided limit? Doesn't exist, right? Because our one-sided limits don't agree with each other. And then we also have f of -4, which is what can we say about f of -4? It's undefined, right? Because there's no filled-in dot that corresponds to our potential function value, so undefined. So in this case, well, we definitely don't have continuity here because we don't have a function value. So let's see what kind of discontinuity we have in this. So if we take a look at what of the 3 types of discontinuities we have, which one would it be here? It's a jump, right? Because the one-sided limits exist and are finite, but they don't agree with each other. So in this case, we have a jump. Okay? So that's -4. So now let's, for the time being, skip -3 and jump, no pun intended, to -2. So we have the limit as x approaches -2 from the left, limit as x approaches -2 from the right, limit as x approaches -2, and then f of -2. F of x, f of x, f of x. Okay? So, what happens here? So, if we approach -2 from the left, well, it seems like we're getting arbitrarily larger and larger as an arbitrarily large positive value if we get closer and closer to -2. So if that's the case, what does that tell us about our limit here? Well, let's give someone else a chance. It would just be infinity, right? So in this case, it's not approaching a finite value. So the best thing we can say is it just shoots up to to positive infinity. Sorry. All right. Then what about the limit as x approaches 2 from the right, or -2 from the right? So what happens here? Yep, negative infinity. Good. Shoots down there. And then that tells us that our general two-sided limit is then
Infinity?
Is it? These two don't agree with each other though. Doesn't exist, right? And then f of -2 is undefined, right? Okay. So if that's the case, well, again, we don't really have any type of continuity here. So what would our discontinuity type here be? Vertical asymptote. Good. Vertical asymptotes. Okay. Now, the last one I want to do with you guys, just as a class, is c equals 0. So if we do that, so we have limit as x approaches 0 from the left of f of x, limit as x approaches 0 from the right of f of x, limit as x approaches 0 of f of x, and then f of 0. Okay? So again, let's focus on our left side limit. So x approaches 0 from the left. What's our corresponding y value? -2, good. Approach 0 from the right, we get -2. And then the corresponding two-sided limit would be someone else? -2. But f of 0 itself is what? Undefined. Good. Okay. So our function value is undefined, so that should be a good enough indication that we have a discontinuity. So what would said discontinuity be here?
Hole,
A hole, right. Why?
because the point isn't the limit, not actually the point.
Yeah, right, because remember, the two-sided limit exists, but it doesn't agree with the function value for whatever reason. In this case, just because it's undefined. So, okay. So, those are the 4 I wanted to do with you guys. So what I'm going to ask you to do now is do the same thing on your own for the other 4 values of C. So in this case, I want you to do the analysis we just did for 4 values of C with the other 4. So in this case, I want you to do -3, +3, 5, and 8. So look at those values of C on your own, and we'll reconvene in about 5-ish minutes. So, okay, so have at it. Is everyone else still looking at the? Still looking at this? Okay. So here's what we'll do. So for -3, let's go ahead and ask someone from this first row here to help me fill in those 4 values. So for -3, what would the left side limit be?
It'd be 2, right?
Yep, it would be 2, correct? Right side limit?
The infinity? For,
Right side limit for -3?
right. It'd still be 2.
Yeah, it's still 2. And then the right, and then the two-sided limit, somebody else from that row?
Two.
2. And function value? And what would the function value be?
It'd be 2.
2, right? So that would tell you that, what would that say about continuity / discontinuity? So first off, do we have continuity at -3?
Yes.
Good. And remind me why again? Look back at the definition. So, remember, what was the big thing we had to remember regarding continuity? What was like the big thing we had to focus on about these 2 values? So for continuity, what was the big thing we had to say about what these 2 values had to satisfy? The limit and the function value have to be
The same.
same, right? So since they are, we have continuity. So. All right, now let's do the same thing for +3. So let's pick on someone from the second row. So left side limit will be? It would be 0, good. Right side limit?
0.
0. Two-sided limit?
0.
And then function value?
On the 5?
Is it? And at +3? At +3, is there a function value? Yep. It's just, in this case, it would be 2, right? Because that's where the corresponding y value is. So in this case, do we have continuity, or what would the discontinuity be here? So continuous, whole, jump, or asymptotes. It's a whole, right? Because in this case, the two-sided limit exists and is finite, but it doesn't equal the function value. So in this case, we have to have a whole. Okay. Now let's take a look at +5. So let's look at someone from the third row. So the left side limit will be what? Positive infinity. Right side limit? Two-sided limit? And then someone else from that row, f of 5? Undefined. Good. So as a result, the type of discontinuity we have is? Vertical asymptote. Good. Okay. And last but not least, left side limit at x equals 8. 1. Right side limit.
-1.
Two-sided limit. F of 8? 1. Right, because that's where our filled-in dot is. So in this case, that tells you that in this case, our limit does not exist. So in this case, that we will have to have some type of discontinuity. So what would that be here?
Jump.
The jump, right? And remind me why? So,
There's space in between, like that too.
yeah, so there's space or jump. But more specifically, the one-sided limits exist and are finite, but they don't agree with each other. So the two-sided limit does not exist. So those are the answers for the other four values of C. Okay, any questions on that? Okay, well, that's all I have for today. So enjoy your 8 extra minutes of freedom on your Friday, and I will see you guys on Monday. Oh yeah, make sure you clean off your tables before you leave.